All right, fantastic. And can you see me?
Yes.
Okay,
Yes.
fantastic. Yeah, so my name is Lane Schwartz. I am here at the University of Alaska Fairbanks. This is work with Coleman Haley, who's currently at Edinburgh, and Francis Tyers at Indiana. I first want to thank everybody who's been involved in organizing this. This is a fantastic workshop, and I'm really glad to see it here. And I want to echo everything that our keynote speakers said at the beginning. One thing that I've really been trying to do in my own work is work on decolonialization. And I think that as we work collectively with Indigenous communities, it's really important for us to look at the ethics of do no harm, being cognizant of the history, working for the benefit of the communities, and being accountable to the communities that we work with. So to start with, I want to acknowledge that I here in Fairbanks am on the land of the Dene people of the lower Tanana River. And it's really important to acknowledge the places that we work and the people on whose lands we live and work. So we've talked a little bit about centering, we've talked a little bit about models. So here's a model of the world. So I'm here in Alaska on the edge of this map. You're somewhere on this map, and there are issues. There are model errors here that we see. This is a very common map, but at the same time, it has massive distortion. So Greenland is not actually the same size as Africa. It's nowhere close. So let's recenter. And here's a different model that I like a lot better. It's a lot less distorted. It has its own issues. There's white space all over the place, but I can deal with that. That's okay. And coincidentally, it happens to center the place where I grew up, St. Lawrence Island, Alaska, which here's another view of the native languages of Alaska. I'm living in the Tanana area and working on St. Lawrence Island. So when we're centering the Indigenous peoples with whose languages we're working, these R words are really important: respect, responsibility, relationships, and reciprocity. And it's in that context that I want to frame my work here. The work that I'm presenting here today on a mechanism for going from interlinear glosses to word embeddings is essentially a foundational technology that we can potentially use in language technologies that are designed to be beneficial to the communities that we work with, and on tasks, such as several people have mentioned already, that are wanted by those communities. So let's do a really quick run through of what are word embeddings. We all use these in all of the modern NLP approaches. Here's an itty-bitty corpus, single sentence in English. It's important to name the languages that we work with. So this example is in English, which is a Germanic language in the Indo-European language family. So if we've got this corpus, the first step that we usually do in translating a corpus into embeddings, it's a training process. And the first step, we usually don't think about this, but we translate each of the words into an integer. Here we've got just 1 through 7. So even in this itty-bitty corpus, in this high resource language, we can see that there's a problem that we're going to run into really quickly, which is we've got 2 instances of a single word here, the, that are orthographically different in terms of casing. So capital the, lowercase the. So this typical approach treats these as separate words. So lowercase the and uppercase the are given different indices, 1 and 5. And so our models by default for a very long time just treated these as completely unrelated types. So we can see this problem in even more detail if we expand this corpus, double it in size to a second sentence that's very, very similar. What's different? Well, we've got dog changed to dogs, so singular plural. We've got street to streets, singular plural. And if we're lucky, some of our current models might have subword, might be subword aware, and might be able to pick up on the fact that there's an S morpheme here that is common between these two. Many of the models wouldn't do this. If we're lucky, the models will. Oh dear. And I just, excuse me. Okay, can you see my screen again?
Yes, it's okay.
Oh, so sorry. Okay, right. And then we've got ran versus run. Now, again, this is in English, and we're hitting an issue that our models probably aren't going to do very well on, which is this vowel change in the middle of a word. So this is really common in Germanic languages, of which English is one. And our typical approach is just learn embeddings. Just give it a big corpus, give it tons of data, and it'll just learn the embeddings. BERT or whatever our favorite model variant of BERT or other model is. Okay, so does this work? Well, yes, for English, for German, for French, for Spanish, for Portuguese, for Chinese, for Arabic, for Japanese, for about 100 to 200 languages out of about 7,000. So even if we do the most aggressive cross-lingual training, fine-tuning, et cetera, there's only about 100 to 200 languages on the planet that have enough data to be able to successfully use this brute force approach out of about 7,000. Interlinear glosses, on the other hand, we've got interlinear glosses for about 7,000 out of 7,000 languages. We might only have a single word or like 10 or 100 words with glosses, but we've got something. So why not use that as the starting point for bootstrapping our embeddings? So this is similar to astronomy. Some of you may have heard me give this example before. So there's about 1.2 times 10 to the 23rd stars in the observable universe. And by sheer cosmic coincidence, that's the same number of potentially morphotactically well-formed words in the language that I work with. So we really have a modeling resolution issue. We need to model stars rather than modeling galaxies. By modeling words, we're essentially modeling galaxies and ignoring the stars and hoping that if given enough data, it'll be fine. What we need to do instead, I'm arguing, is model morphologically analyzed words, and that this will give us a lot more power to work with so that we can use the linguistic structure that we've got in these interlinear glosses as the starting point for meaningful, interpretable word embeddings for all of the world's languages. So for the rest of the talk, I'm going to go through some examples of interlinear glosses and show what we can do using this tensor product representation approach that's mentioned in the paper, that we talk about in this paper. So here is a way of visualizing the interlinear gloss for dog versus dogs. We've got a lot of really rich information here. We've got the orthographic form, the orthographic surface form of each morpheme, including a null morpheme for the singular, for the English singular morpheme, which it doesn't show up here in the surface form. We can show other things like the fact that we've got the phonemes for each of these letters as well. So let's take a look at a slightly longer word. We went from dog and dogs to this long word. This word is from St. Lawrence Island, Yupik, or Akuzupik. So this is a polysynthetic suffixing language, and this is the interlinear gloss for that word. So it translates as, I didn't want to make a huge house. We start off with the base noun house, and then we've got 4 different derivational morphemes that change this from house to big house, and then build a big house, want to build a big house, don't want to build a big house. And finally, we've got the inflectional morphemes for verb mood and person number that tell us that it's I didn't want to make a huge house. So our approach here is using tensor product representations, and I'll point you to the paper for the mathematics behind this, but the basic idea is that we're going to be able to take each of the aspects, each of the pieces of information that's available in the interlinear gloss, and then explicitly encode that in a deterministic manner as a vector. So vectors saying M is the first word in this morpheme for house. A is the next letter, and so on. We can explicitly encode the orthographic form of each morpheme, including both the underlying form and the form that surfaces in this particular instance, as well as, for example, the phonemes that correspond with those. We can encode the morpheme identity of each morpheme, as well as essentially the part of speech of each morpheme. So is it a noun root? Is it a verb root? Is it a derivational morpheme that starts with a noun and ends in a noun, or starts in a noun and ends in a verb, or a verb-to-verb derivational morpheme, and so on, as well as the inflectional endings. So most of the work that's been done in computational morphology that you see, for example, in Sigmorphon, has really focused on inflectional morphology, which is very understandable. But this approach allows us to seamlessly encode not only inflectional morphology, but also derivational morphemes. So is that cool? And also potentially extremely helpful in overcoming vast data sparsity issues? The corpora that I work with are on the order of tens of thousands of tokens. And if you've got tens of thousands of tokens, you can't brute force things, especially in a polysynthetic language with so many word forms. So is that cool? Abso-fucking-lutely. So here's an example. Why am I bringing this up? Because this is an example of another really interesting morphological phenomenon, infixing in English. We don't think of English as having infixes, but it absolutely does. There's this intensifier, this expletive intensifier. And here's the interlinear gloss for it. There's a really famous paper that talks about just this, expletive infixing in English. And so we've got the adjective root, absolutely, and then the intensifier that is infixed in here. And we can encode not only all of this other information, but also the structural relationship between the morphemes. So words now with infixes, and we can encode this. What else can we do? Well, we can do circumfixes. So Chukchi is another indigenous polysynthetic language. And here's an example of associative case that's marked with a circumfix. We can handle that in exactly the same way. We can seamlessly handle reduplication, such as that is very, very common in Malaysian and Indonesian. So here we're encoding the plural morpheme, as well as the fact that for this particular example, the plural morpheme surfaces as a reduplicant of the noun orang. This also allows us to seamlessly handle templatic morphology in exactly the same mechanism. So here we've got Maltese, a singular and plural variant of the word for book, and we're able to encode all of this nice information from the interlinear gloss, including which characters in the word are associated with each morpheme. So with that, I'll say is which is, oh, how one has become thankful in St. Lawrence Island, Yupik. Thank you very much. And with that, I'd be happy to take questions.
Thank you very much. It was very interesting. It was just some time. So do we have questions here or in the offline section? Okay, I'll ask the first question. I wonder if like some suprasegmental morphology, some like tonal features can be encoded with this method.
Sure. So can you give me an example?
Well, I just thought about the languages where like the word forms are generated with tones, for example, which are applied to the original root, to the original stem. I can't unfortunately give you
Sure. Yeah. So let's. I mean, we could think about this in terms of like ran versus run in English.
Oh, okay.
Yeah. So I mean, this isn't tones, but it's the same kind of thing. So the short answer is yes, you could, but the longer answer is this really comes down to how the linguist would describe it. So the general mechanism that we're using here is if you can come up with a set of feature value pairs that the linguist would use to describe what's happening, then we can encode those feature value pairs in the tensor representation. So really the answer comes down to, well, how would you do this by hand? How would you do this in an interlinear gloss? And that's where the challenge comes down to. Going from whatever paper and pencil representation you have to the electronic representation is relatively straightforward. But yes, if you can come up with a way of encoding this that you would represent on paper, then you should be able to use the same mechanism electronically.
Okay, thank you. That's nice. We've got a question, František.
Yeah, thank you, Lane, very much for your talk. It's very, very interesting, inspiring. I wanted to ask, how do you deal with the IGT? So you string the morpheme in the language you're working on together with the gloss and take that as a chunk that you then work further with. Is this described in your paper also or elsewhere?
Yeah, so the way that we have dealt with this to date is slightly more simplistic than what I've shown in the slides. In practice, what we did was we took a finite state morphological analyzer and used that analyzer to segment into morpheme boundaries, and then used a simplistic representation where all we're representing is the orthographic surface form of each morpheme, as well as the morpheme identity. So to go beyond that to these more sophisticated things, more sophisticated models that I showed here, again, conceptually, it's not hard. You're just going from whatever feature value pairs are in the interlinear gloss to the tensors. But to do something as rich as here, you would need a front end that would take your interlinear gloss and translate it into the feature value pairs in such a way that you could then create the appropriate tensors for that. So
but you don't have this yet, do you?
I'm sorry.
You do not have such a front end yet, or you're building something like that?
Our front end is not that sophisticated yet.
Okay.
I'm hoping to extend this into a more general front end, but that is future work.
Okay. No, I'm asking because you know the IGT issue. There is work by Emily Bender and her colleagues from University of Washington on the Zeit format, which kind of fixes this quite nicely.
Yes, I'm very aware of that, the XIGT format. Yeah, and coming up with the XIGT to TPR, I mean, that would be a very straightforward extension of this.
I've been working on something like this with some mathematicians where we have been trying to, deal with the galaxy problem on a different language. I will be talking about it later, but not about this today. And so I'm finding it very interesting. Maybe we will exchange some emails later.
Please send me an email.
Yeah. So thank you very much.
Yeah, absolutely.
Thank you very much.
Yep, thank you.
So if there are no more questions, so I would like to thank everyone who was in this section. I would like to thank the speakers once more for their very interesting and important talks. And I would like to thank the audience. And I think that we're going to have a break now. And so the next section will start in 20 minutes, in 24 minutes. It will be the poster session. So thank you very much again.